A very good morning to one and all. Welcome to the session on simulating band gaps and scattering in phononic crystals with COMSOL multiphysics. So myself, Antis K. Martin, and I will be the host for today's session. So today we will be having the speaker, Dr. C. Chandraprakash. So I would like to give a brief about the speaker. Dr. C. Chandraprakash is an assistant professor of mechanical engineering at IIT Kanpur, India. His current research interest includes computer vision, multifunctional material, acoustics metamaterial, thermal and ultrasonic non-destructive evaluation, and biomimicry. He received his BTech and MTech degrees in mechanical engineering from IIT Madras, India in 2010. After graduating, he worked as an engineer with Tata Motors, Pune, India, before going on to earn his PhD in engineering science and mechanics from Pennsylvania State University, USA. So as of now, we know that actually we have the best speaker in India right now. So we will be having a fruitful session. So first of all, thank you so much for accepting our invitation for this such a fruitful session. So I would like to hand over the session to Dr. Chandraprakash. Sir, over to you.
Okay, thank you. So first, let me start sharing the screen. Is my PowerPoint visible?
Yes. So maybe you can go
so
for
I've got a full screen. I'll turn off my window, my camera. Okay. All right. So good morning, everyone. First, let me begin by thanking COMSOL for giving me the opportunity to give back what I have learned over the last good number of years simulating elastic waves and acoustic waves. So let me get to the full screen mode and let me start. All right, so we will look at how to simulate or how to compute the band gap and the scattering in phononic crystals, or largely you can extend this to acoustic metamaterials. So first few minutes we will spend as to why we should do this and how we should go about doing it. And as we go on, then I will try to show you a few examples in COMSOL. If possible, I'll try to run them live if time permits. Otherwise, I'll just walk you through the models, and those models also will be shared with COMSOL later on. So as we speak, the last ever since I think 1993, the first phononic crystal was envisioned, and then now fast forward another 30 years, we have a series or variety of acoustic metamaterials. They're quite different from the existing acoustic materials that we see around, including those sofas and chairs. All of them have these spongy structures. Those were the classical ones, and now you see all these various kinds of solid fluid and labyrinth kind of structures, a lot of them. One of the earlier versions of it is the phononic crystal. What is a phononic crystal? An easiest way is something that is a set of solid or fluid materials which are arranged periodically. This architecture is one such thing. A bunch of matchsticks could be treated as a parallel array of sticks. And since they are sort of periodically arranged, they can be envisioned as also as phononic crystals. Essentially a periodic medium where you are interested in studying the elastic wave or the acoustic wave propagation. So phononic crystals is a subset of acoustic metamaterials. So this largely is about the study of elastic waves. Refers to the waves in solids. Acoustic strictly refers to the waves which propagate in fluids, that is in liquids and gases. So the idea of why one should do this it's phononic crystal, not phononics crystal, is that you want to control waves which are otherwise not possible in the regular materials. What are the regular materials? The stainless steel, the wood, the polymer, the HDP, LDP, and so on. You want to structure the materials such that you get what you want to get. And the common methodology is to use periodic medium. What is periodic medium? I say A followed by B followed by C. Then again a repetition of the same ABC, 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 and so on. And you can combine, you can also make A within A, you can put one more A prime, within B, you can put one more B prime, and so on. So you can use a combination of materials. So geometrically, they are periodic. The key characteristics is primarily band gaps. We'll see what it is, and focusing and so on. Once you have a band gap, then you can tamper, I should say, and make it into a waveguide or even make it into a collimator. And the primary application is, since there is a band gap, it's going to throw back the waves. It's not going to allow it to go forward, right? And always there are, you can have this same phenomena in low frequency, which is in the sonic regime, or in the intermediate frequency, which is ultrasonics, or also in the hypersonic regime. Right. So phononic crystals, I've been saying periodic. So what is periodic? This is a classical image which is taken from the book by John Jonopoulos on photonic crystals. The material distribution is the same for photonic as well as phononic crystals. So here what you see are these three simple versions of periodicity in the three dimensions, right? A set of slabs, a set of pillars, and a set of cubes, nicely arranged in a periodic fashion. And you can always say, okay, I can study just one unit cell. We'll see why you should just study one unit cell. So, but what is the fancy nature of fancy, or what is so good about or bad about this phononic crystal? What is the key characteristic? The key characteristics is this. Let's say you're talking about this two-dimensional, I don't know if a mouse is visible. Let me pull out the pointer. Right, do you see the pointer? Yeah. So if I take this two-dimensional phononic crystal, and if I send in waves along X or the Y direction, and not in the vertical direction, say, and let's say they have 8 such pillars, 8 of these red kinds or 9 of such red kinds. And if I send in waves whose wavelength is roughly the order of the period of this phononic crystal, then what you would notice is that there is a small spectral regime in which waves do not pass at all. What is transmittance? I'm sending in something and I want to measure something on the other side. So if you simulate or even if you measure, you will see that for waves of a particular wavelength regime, frequency can be translated to wavelength, around this wavelength corresponding to the length of the unit cell, there will be no wave transmitted. Everything is rejected back. This is very similar to the good old Bragg's law that we learned in 11th and 12th standard. So the idea is the same. If you have periodicity, there is a particular spectral regime in which the wave does not pass through, and the same thing is termed as band gap. Right. So this is the key characteristic. So what happens if the wave comes back? The wave comes back, basically the wave doesn't go. So it is clearly a band reject filter. Okay. And so this is sort of the thumb rule for the same. You're looking at approximately the ballpark of the wavelength and the of the unit cell are in the same order. That is the region of interest. Okay, so this is the key characteristics, and exploiting this, we can further have a variant of it, many variants of it. One example is a waveguide where you pull out a line of an array, a linear array, or you vary the distances and allow it to collimate, or you sort of gradient them either geometrically or by their number density. Either way you can do this focusing, and there are many more such applications. The key to all of this lies in either measuring or you computing it, and this phenomena has been established across the length scales from nano to micro, milli, centimeter, and even in meters. Okay, so the same set of phenomena exists at multiple scales. The governing equations are the same. And I've tried to put together as to what are the length scales corresponding to each regime and their corresponding applications, right? And this was a recent paper where they have tried to put a equivalent schematic equivalent to the electromagnetic spectrum, the use of various spectrums in phononics. So what exactly do we compute? We have seen now what is an acoustic material, what is a phononic crystal, and we want to study some wave propagation through it. So I see a wave on the left hand side. So what exactly do we compute? So we compute the following. Let's imagine a two-dimensional array of disks in a square lattice. So you can call this as a 2D phononic crystal. And I'm sending in waves. We've already seen that this will give rise to some kind of a band gap. Right? This is what you normally call it as transmittance, or if you take the logarithmic version of it and multiply it by 20, you call it as transmission loss. Right? So this is one, which is you're imagining yourself doing the experiment. Likewise, now why should I send waves only in the horizontal direction? Right now I have sent waves of different frequencies in one direction in this current picture. Now I could as well send waves in different directions. And in different directions, I can send waves in of different frequencies. Right? So we are talking of not just one graph or one transmission spectrum. We're talking of multiple transmission spectrums. So how do you represent them? The easier way to represent them is to add one more axis. Okay, the third axis is going to be the direction axis. Okay, and that diagram is called as a band diagram. And that will give us all the set of band gaps for different frequencies in different regions. So how exactly does that look like? This is how it looks like. So I've inverted I sort of rotated the transmission spectrum. The right hand side figure is the transmittance. Okay, the vertical axis is the frequency. Okay, please note the 0 is here. So I've sort of how did I rotate? I rotated by 90 degrees clockwise. So that's the transmittance spectrum. And this is the corresponding dispersion diagram. So gamma x is one such direction which is the horizontal direction, which we have just what was shown in an earlier slide, where the region between 0.2 and 0.35, we see that there's no transmittance. At the same time, in the corresponding dispersion diagram, you see that there are no waves. There is no value of frequency. This basically means there's no wave which is going forward. So for every minimum, in every minima in transmittance, you will see that there is correspondingly no intersection of bands in the left-hand side diagram. So in the left-hand side diagram, each line is called as a band. If you take the slope of it, if you take the slope of this particular line originating from gamma towards x, if the slope of this line will give you the phase speed, omega by k is this phase speed. So this is the full picture. Transmittance is going to tell you, is going to be of more use for field measurement. The dispersion diagram or the band diagram shown on the left is going to be of give you a more holistic picture as to in which direction should I send the wave and what is the range of band gaps that I can see. However, what the left hand side will not tell you is the extent of transmission for which you need to compute. And transmittance, reflectance, okay, all these terms come under the broad area of scattering. All right, so let's proceed. So now let's ask this question as to why should I use FEM or COMSOL, and then we'll go on to implement things in COMSOL. Okay, so why FEM? Main reason is there are quite a few methods. Okay, band diagrams typically are estimated in frequency domain, and the common methods are like plane wave expansion method, and there's things like extended plane wave expansion, modified plane wave expansion, reduced one, and so on. So there's spectral element and multiple scattering theory. All these work, but you need to write your own programs, and there's nothing wrong about it, just that they are usually time taking. Likewise, there is finite difference time domain. So the time domain technique. Time domain techniques usually take larger computer memory and time. Likewise, say we have this integral methods, which is finite element, boundary element, and we will check. We'll work through finite element today. And recently, there's a push for meshless methods too. More such hybrid methods are also emerging. However, there's a limitation to some of the techniques which I mentioned. For example, plane wave method, which is widely used, will not work if you have both everything as even if one of them is solid and one of them is fluid. So they have their limitations, and Fourier transform has the numerical implementation of Fourier transform goes through a phenomenon called Gibbs phenomena, where as the difference in properties of the materials increases, the inaccuracy starts to increase. Okay. Finite element has its advantages. Mostly you don't have to write your own program these days. The second one is there is a large amount of modules that are available, a large number of options which are integrated into a software such as COMSOL, and you can do a lot of complex geometries. And as an engineer, you want to get to the correct, you want to use the tool and get to the solution correctly and preferably faster. So in that sense, FEM sort of becomes very handy, and I found COMSOL to be quite useful there. So what do we need to simulate things in COMSOL? First, you need three things. One, you need the base package, and then you need the structural mechanics, which takes care of the waves in the solids. The second one is waves in fluids. This is an essential part. Should I do it in time domain or frequency domain? You can do it in both. Okay. Frequency domain is relatively faster, especially when you're computing band gaps. Okay, you can as well do it in time domain. There's nothing incorrect, just that you will end up for transmission loss. It may be the time of computation may be the same, but for when you're computing the band diagrams, the time to compute in frequency domain is far lesser. So let's begin by assuming that we are doing in COMSOL. So I'll start with a very simple example: a bunch of cubes arranged in a cubical lattice. I'll try to show you two different views in a two-dimensional plane. Here are the screenshots of the same. So you can say that this is a simple cubic lattice where the scatterer is the sphere and the host is the surrounding material. So this is a terminology which I would be using. Whatever is embedded is the scatterer. Here the scatterer is the sphere, and the spheres are embedded in air, water, whichever is the surrounding medium. The surrounding medium is called as a host. So scatterer and host. So theoretically, when you say a phononic crystal or a photonic crystal, they are assumed to be infinite. But I don't need to work with an infinite thing, because whatever is happening on the 79th sphere will also happen on the 80th sphere, will also happen on the 67th sphere, will also happen on the 37th and the 12th and even the 6th sphere or the 6th scatterer. So in that case, I don't have to compute all the 1,000 or a million set of spheres or the scatterers. I'll simply take one representative of it, and that's called the unit cell. And we're going to work with this unit cell. If I have to work with this, if I have to compute these band diagrams and band gaps. Likewise, a common thing which people study is this wood pile structure. The structure shown in figure B. This is done by one of my students, Siddharth. So here what he has shown is a set of wood logs arranged horizontally, and then again the next layer they're arranged by rotating it by 90 degrees, and then this pattern repeats. This sort of a pattern is called as wood pile structure, and what is shown in A is the unit cell of the same. And what is C? C is the Brillouin zone. We will get to there in a minute. Okay. So how does the computation for transmittance or transmission loss vary? Let's say this is my unit, this is my phononic crystal. I made it finite. Ideally, a phononic crystal is infinite in all the dimensions. I made it finite. I want to study waves going along the y direction. So, but I do know as I go along the x direction, whatever is happening on the second one should happen roughly on the fourth and the fifth and the sixth and seventh and so on. So the thing should be the same along x. I'm sending in a wave or an energy along y. There's no reason for the geometry to be altered along x. So for that reason, I'll keep the wave. I mean, wave is something which you send externally, so that can't be played or tinkered around with. And I'll choose this kind of a unit cell. I want to study waves along y. So along y, I'll keep as many scatters as I would like. And along x, I truncate things, and I'll use what is called, I'll say they are periodic along x, just the way we have done for band diagrams. Likewise, imagine an array of helices, springs rather. Okay, some helical structures, I have arranged them periodically on the xy plane. So this is a three-dimensional phononic crystal. It is periodic along z, and by position of the spring periodically in X and Y, it is also periodic in the horizontal plane. So this is a fully three-dimensionally periodic unit cell. If I want to study the band diagram, then I simply need to take the right-hand side diagram and take just one period of the helix. I'm good. However, if I want to study the wave propagation along Z, I would have to choose such a lattice which is long in Z, and that is periodic with periodic conditions applied along the X and Y directions. I'll show the implementation. I'm just showing how do you translate your realistic picture into a computational picture. To compute, what do you need to do? You want to compute for whatever is shown on the figure on the left, however you work with just a condensed version of the same figure. Right. So what are the governing equations? So the governing equations are the very standard ones. You can actually in COMSOL, you can actually do more advanced versions of it. I am sticking for this seminar, I'm only sticking to the linear materials. Material response wise, they are linear. You can as well include geometrically nonlinear response. There's more to it. So essential things, you need the kinematics. What kind of strain were they using? This is the what I'm showing is here. Here is the Cauchy infinitesimal strain or the small strain. So this is the linear strain. Okay, you can add in plastic strain. You can bring in green Lagrangian strain. More complicated versions of strain, as in when how your geometry demands or your material demands. Next is the three things. One is kinematics, second is constitutive relation, and third is the force balance. The constitutive relation for linear materials is this, with the elastic or the stiffness matrix being symmetric. So you will have at maximum of 21 constants. And you can do more advanced versions, like I said. You can add a bit of plasticity, nonlinearness, viscous nature. A lot of things can be added. But to begin with, let's start simple. For an isotropic solid, you know the standard form, which is in terms of lambdas and mu's, and which are also related to the Young's modulus E and the Poisson ratio nu. The last equation is the force balance, which does not change regardless of whatever material model that you choose. Del dot sigma plus any body force is basically going to be the acceleration. Right, and you often band diagrams, and in one of the earlier slides, I've shown you phononic crystals at different scales: nano, milli, micro, centimeter, and even meters. The physics remains the same. So often you end up scaling up things. If you want to study a meter long, it is as good as studying a millimeter size in computation domain. So you often end up scaling down your frequencies by these phase speeds. So that's the reason that you can compute in whichever direction. This is in the standard X, Y, Z directions that I've shown here. Likewise, in elasticity, there's solid and fluid. Here I'll directly go to the point. We have already defined the kinematics. So the key thing is a constitutive relation. So you have the hydrostatic pressure P, the shear the shear viscosity and the bulk viscosity. And since you're doing waves, you do a first order perturbation. Rho prime indicates the perturbation, and then you have this conservation of linear momentum. So this is essentially the equation that you would be solving or implementing in COMSOL. So let's begin by computing the band diagram. I'm assuming everybody now still remembers that two-dimensional array of scatters, which is a 2D phononic crystal. So here I'm showing the unit cell of the corresponding phononic crystal. So I have an S represents the scatterer, and I have a linear array. So I have scatterer, scatterer, scatterer in X direction as well as in Y direction. There's an array of it. I'm only going to work with the unit cell. Okay, so I have the dimensions are all listed here. On the right hand side, what is shown is the Brillouin zone, which is the area between the points gamma, X, and M. What exactly is the Brillouin zone? I think this was a very nice reference which I have listed here of Professor Pratap Haridas. If you need the basics, you can go in there. So let's say the host is fluid to start with, as an example. It has acoustic waves and it's governed by the Helmholtz equation. And I'll take a simpler isotropic solid as a scatterer, and it's governed by the Navier equation. Right? So what exactly is this? Is a geometry. These are the domain equations. That's fine. So how exactly I'm going to call it as a unit cell by enforcing this floppy block periodic boundary conditions. Essentially, what you're saying is whatever is happening on the left is roughly the same, or not roughly. It's the same thing must happen on the right hand side. Same thing, whatever is happening, if it is also periodic along the y, whatever is happening on the bottom face must happen on the top face. I'm saying face, but you can also imagine as a 3D. Here it is an edge, right? That is all there is to it. Further, since you are dealing with solid and you are dealing with an interface of the scatterer and the host, the boundary between H and S, there the conditions are velocity being continuous, velocity normal to the interface being continuous, and traction also is continuous. So this essentially covers all the governing equations. The domain equations are Helmholtz and Navier. Outside the unit cell is the floppy block, and at the interface of, since we have fluid and solid, it's velocity continuity in the normal direction and traction continuity. This is all we are going to implement there. If you have to do transmittance, like this is the schematic. Left side is what you actually want to know of. You take the right hand side and that's what you compute. So how do we do this? I'm showing you two different diagrams. Okay, there's a reason for it. We'll get there. I'll walk you through this. Now, PML, first thing let us understand, is a perfectly matched layer. Okay, what does it do? Think of it like a cushion. Whatever comes in it, it absorbs. Okay, think of it the equivalent of a black hole. Right, that's the whole point of it. It is not going to reflect anyway. Whatever is thrown into it, it's going to take it and it's going to absorb those waves. So you don't want any back reflection from it or through transmittance from it. So the host is shown in yellow and the scatter is in blue, something which I think we are all now on the same page with. In the first case, I will say that the scatterer is a fluid. Okay, the whatever is shown in blue is a fluid. And in the second case, the scatter is a solid. It so happens that when you want to put in a pressure wave, when you have typical transducer sends in a pressure wave, or you can also send in a shear wave. Okay, in that case, you can probably put in a more thicker liquid. But if I focus on the first one, it does not matter. The host is the yellow one. Okay, please focus on the top figure. The host is in yellow and it's a fluid. In the second case, the host, which is the yellow region, is a solid. In that case, I'm wanting to send longitudinal wave, and it's easier if I have a liquid. And for that reason, I put in water because I can easily give the pressure as the input. On a solid, it is not easy to give pressure as the input. You can probably give traction as the input. That's one way. But since you want pressure, direct pressure only, I can give in. That's the reason I chosen to put a layer of water, just so that I can feed in the pressure. That is all there is to it. Otherwise, I didn't geometrically or schematically they are the same. I'm sending in waves from, say, here the left hand side, and I'm catching and computing things on the right hand side to see what is the transmittance. And at the plane A prime, I can compute whatever is reflected. Everything is possible, but the schematic is the same. And what is new? The domain equations are going to be the same, the Helmholtz and the Navier, or even the Christoffel equation. On the top and bottom side, I'm going to implement the periodic condition, the floppy block periodic condition. On the left hand, right hand side, I'm anyway governed by the perfectly matched layer. So the same thing goes with even the case of a solid solid. All right. So whatever we have now sort of walked through, in a few minutes, we'll see all these cases. Okay. In science, there is no suspense, so I'll sort of show you the results, and then we'll go spend some time in walking through the COMSOL models. Okay. The crux of it, one is to know the theory, and the second thing of finite element method, through my experience, what I've learned is the science of meshing. It helps if you there's a reason I've put this in big font and put this in separate slides, so that later when you want to implement, you can probably choose this as a standard operating procedure and get these things done. So whatever I've shown you here, I will actually show that to you in a COMSOL model. So these few slides are for your long-term reference if you wish. Okay. So let's go there. So roughly this two-dimensional model, the mesh looks this way, and 3D also I've tried to show here, or for a helix and a chevron. And for a transmission, or for the calculus, for the calculation of a transmission loss, or transmittance or transmittance spectrum, whichever you choose to have. This is made by my student Siddharth. Is currently doing his PhD in Netherlands. This is the transmission loss diagram for if you have to compute for a wood pile structure. What was a wood pile structure? It's worth going back once again. So let me just get out of the screen. Okay. What was the wood pile structure? This. Okay, there's a slight delay, I think, in the way it is showing up here with what I'm clicking versus what is shown here. Yeah, I guess now you should be able to, yeah. So this was the wood pile structure. Remember, there's a bunch of logs in one direction. The next layer, the logs were in the other direction. So for this case, it's carefully made. This diagram. Okay, I think the screen takes a bit of time for you to show up there. So this is the corresponding three-dimensional diagram with PMLs when I want to compute for a three-dimensional phononic crystal, the transmission spectrum. Right. So the next, let's go on. The next important detail is the solver. One is meshing. Well, first is the theory, second is the meshing, and the third is the solvers. What kind of solver should I choose for which kind of problem? Again, as a reference or slash manual or a standard operating procedure, I put together what should be done if you are seeking eigenfrequencies around, say, 1 megahertz. Okay, essentially, what are we asking COMSOL to do? Okay, that's the key, or how exactly are we going to do it? This is what we are asking COMSOL to do. The whole idea of a band diagram was I want to send waves in different directions, and in each direction I'm going to send waves of different frequencies. And I want to know in each direction what are the waves that go through and what are the waves that don't go through. An eigenvalue problem does exactly this. Say I'm sending waves from the left side, and on the right side I have my receiver. The receiver, if it is not receiving a set of frequencies, those frequencies will not show up in the eigenvalue problem. The eigenvalue problem will capture or will tell you what are the frequencies of waves, or what are the waves of certain frequencies that actually pass through, and that is all it will compute. Whatever it does not compute is the band gap. Okay, and just that we are doing that in the reciprocal space, and we compute. It is sufficient to compute along the edges of the Brillouin zone. And how do you compute the reciprocal space? The reciprocal space is computed using the standard vector algebra. Square lattices, the thing is straightforward. You have unit vectors along I, J, and K, and your reciprocal vectors are also along I, J, K. Things are relatively straightforward, which is why I did not touch base upon them. A triangular lattice is something which is trickier compared to a square or a cubical lattice. So which is, and triangular lattice you can compute in different people compute it in different ways. So I can choose my unit vectors like I've shown here, and this is one way. Okay, and the corresponding points in the Brillouin zone are also have indicated gamma, K, and M. Likewise, so this is the first style. I choose one along the x-axis and the second unit vector, which is at a 60 degrees from the x-axis. And you can compute B1 and B2. Correspondingly, using the Brillouin zone, you would identify the points gamma, K, and M. And once you do that, remember we said we're going to say compute or identify the frequencies which are good enough, frequencies of the waves which are good enough such that the waves can go through. And to do that, gamma m is one direction, gamma k is one direction, km is another direction. So the three directions when I'm talking about a two-dimensional triangular phononic crystal. So this is exactly how you do it on paper, and then you feed it back into COMSOL. Okay, the crux lies in getting the Brillouin zone, identifying the points, and doing this vector mathematics to tell COMSOL how do you feed it there. Okay, likewise, now here I chose two different ones. I'm saying one is at one unit vector in my real space is at plus 60 and other is at minus 60. Okay, but you can again compute v1, v2 and the corresponding gamma k and m, and then sweep along each direction. And likewise, you can have, sometimes it is, you will be constrained to choose along a particular direction. You may not have the luxury to always go along 0, 60 or 60 minus 60. Sometimes you may have to go to 60 and maybe 120. Okay, that will happen when you have a chevron kind of lattice. Okay, accordingly, you'll have to choose your unit cells. And for the cases which we first saw, this case of a simple cubic lattice where the scatters were spheres, this is the standard. This is something which is now very common. And one luxury which COMSOL gives you is that you can actually feed in complex properties and get complex eigenfrequencies too, which have their own separate meaning. Okay, so coming to solvers, when you choose identifying when you're computing transmission loss, you do a frequency sweep. When you're doing band diagrams or band gaps, you choose an eigenfrequency. The solvers are different. The mesh and solver settings I have detailed in this particular work. I have also given the same in the earlier slides, so you can follow either of them. Let's see the results. And whatever a software or COMSOL model gives you, how do you know that it is accurate or correct? That begs the question, I mean, how good or how reliable is your result? So I've chosen few simple cases from literature, like steel, sphere, and an epoxy cube. Okay, I'm talking about a unit cell. I have a unit cell, which is epoxy, and inside which I've embedded a steel with these as the properties. Okay, this is something I computed analytically. This is a band diagram, and the same thing I try to compute in COMSOL. Okay, so you would see that it's the same. In fact, since I've done differently in different directions, I chose to have different colors. Likewise, I did another solid and solid. Okay, and I computed using two different versions. This is version 4.4. Then I choose this, computed one more in MATLAB, and then try to do the same thing in COMSOL with a different version. So in all cases, you'll see a very good match with where analytical solutions exist. But you must recollect analytical solutions are not that straightforward. When you, in fact, there's no analytical solution when one of the scatter or the host becomes a fluid. Right. Then I also showed the triangular lattice. This is from the case of literature. This is the diagram, and it's an identical diagram when I compute it in COMSOL. Okay. You can go for even higher frequencies, but most of the band gaps, in fact, the bands overlap, and you will not see any band gaps as you go for higher normalized frequencies or even higher frequencies. Likewise, I chose one more where this is the case of steel rods in water. This is from literature, and the same identical graph you could have. This is the case of a solid fluid, and I could compute the same. I guess this two-dimensional simulation was taking quite a. I guess it was less than 10 minutes. All the three bands together. Now I'll show you some results on little complicated geometries, which we have done over the past few years. One is the case of where I put in stainless steel spheres in air. Okay, and these are micros, not spheres. Let me correct myself. It's stainless steel pillars, micrometer-sized stainless steel pillars, where we could compute the band diagram and we could also compute the transmittance along a particular direction. And that particular direction was the x-axis. So in the gamma x direction, if you see wherever there is a band gap, okay, each line. Okay, probably I should use a pointer. Yeah. So each line in this left-hand side diagram, which is a band diagram, is a band. You take the slope of this, you will get omega by k. Okay, or here I'm plotting frequency. multiplied by 2 pi and then omega by k will give you the speed, longitudinal phase speed of air. Here is the rate of air. So wherever there is no intersection of bands, that is the band gap, which is shaded in yellow. And the corresponding, the same frequency regime, if you try to measure the transmittance, you will see that you will actually get no transmittance at all. So this confirms a lot of things. Now that I've validated all my things, it is also a reliable result showing, see, I can compute both ways, transmittance and this, and either way, I'm going to get the correct results. So I've tried to play with water and also epoxy. And what steel epoxy is known to have complete band gaps, like I shown in the third figure here. So you can vary the geometry, you can feed in parameters. Once you have validated your solutions, these are fairly quick computations. Likewise, let me show you a slightly complicated case of a helix or a phononic crystal comprising of helices. So this is a three-dimensional phononic crystal, okay, or other way of saying is two-dimensional array of helices, okay, or often called as chiral phononic crystals. Since your scatterer is a slightly complicated shape, correspondingly, depending upon your unit cell, your Brillouin zone also will vary, and you should be able to identify the corresponding edges of the Brillouin zone and identify the corner points over which between which we will compute the bands. Okay. So here are the corresponding computations. In case of a sphere in a cubical lattice, you'll have gamma, x, m, and so on. It's sort of 4 paths. And if it's 2-dimensional, you have 3 paths. But as your geometry gets complicated, or even if your material is anisotropic, you will have multiple paths as shown here. But all of which can be readily accommodated. I will show all the models for all of this. Okay, maybe we are almost done. Okay. So these are some of the references of my own work. The reason for listing is I struggled when I was first beginning to implement the theory into COMSOL and get the results. Took quite a bit of work, but I've ensured that each of those details are documented in these. So those of you who are interested may refer to this and cite appropriately. So these are some of the things, papers that I've shown for the earlier figures. So now let's get into COMSOL, actual COMSOL. So I'll get rid of PowerPoint. Okay, so let me minimize this, and is my COMSOL visible?
Yes, sir, it is visible.
Nina, it's visible. Okay. So I'll try to see. Okay, you are able to see the screen, or do you want me to do any modifications? So this is one of the simplest case of
Sir, actually, we lost your audio. I'm not able
you
to
lost my audio. Let me just reconnect.
Yeah, for some time, maybe 5 seconds actually we lost. Now it is fine.
How about now?
Yeah, now I can hear you actually, but I
Am
don't
I
know
audible
whether.
now?
Yeah, now you're audible, sir.
Now I'm audible, so I'll try not to move. Okay, so this is the simplest case of the case which I've shown earlier, a distribution of spherical spheres in a cubical lattice. So I've defined my parameters. I have only 2 here, radius of sphere and the length of the cube, which is a. Okay, then I go on, build my geometry. Okay, draw the sphere, draw the block first, then the sphere, and then I assign my materials. Okay, so I've chosen a material called parylene, and then I said the ambience is air. All is good. Then this is done using an old model, but I'm able to open it in a later version. So that's one of the advantages, I believe, with COMSOL. So I've chosen for the ambience, which is air, the medium. There I've chosen pressure acoustics. You can actually go on and verify what is the equation that you are seeing here. Okay, what is the equation that you actually implement in the center? When you click on equation, you actually see here, this is the Helmholtz equation. All right. So everywhere, whether it is a domain equation or even here, you'll see the Helmholtz equation, or whether it is the boundaries. So let me go to, we said we are going to use periodic boundary conditions, right? So let's see the equation here. Okay, I hope it's now showing up there, right? So I have chosen a pair of opposite sides here, which are in the x direction. Whatever is selected in green here, 1 and 14, these are these two pairs of opposite sides along the x direction. And I've set periodic boundary conditions, and I've chosen this as block-wave block periodicity. The COMSOL gives you a multitude of multiple options. For us right now, block-wave is good enough. There are other things that you can do when you're doing radial periodic crystals, radial phononic crystals. Okay, so you can choose cyclic and so on. So the equations also are displayed. Right now, I've set everything as kx for demonstration. You should kx, ky, kz. That would be the ideal way, and then control everything from parameters. Okay, let's compare. By default, the boundary condition is COMSOL treats everything as a hard boundary, wherein there is no displacement. And then it gives you a lot of options if you have more things to do. If your geometry gets complicated, like when you're doing other acoustic metamaterials, where you want to put a little more boundary conditions when you're doing it lumped masses and so on. But for the first, just the band diagram, I think you just need to use these periodic boundary conditions. We don't have any special edge points, and solids, it's easier. We have one solid, which is a sphere, and again you can always go back and check the equation. This is the standard Stoffel equation. As I said earlier, you can add in plastic strain, you can add pre-strain. Okay, you can custom define a lot of properties. Okay, and one thing I might have skipped, when you're defining properties, you can actually make here the properties. When you click on properties, you can, right now I've chosen this to be as isotropic. You can make it anisotropic either from materials wise. You can define your material, okay, under basic, you can go and define it here, or you could come to your solid mechanics, okay, and make it user defined. Okay, I can define it in any number of ways. If you know Young's modulus and Poisson ratio, that's one way, or you can even make it anisotropic. Okay, for now I specified the Young's modulus. I'll go from material. Like one of the things I said earlier, you can make it geometrically linear or even non-linear. So the sheet of cloth around us or the paper, those are all geometrically non-linear. Kerchief is non-linear, curtain, all these are non-linear, highly non-linear. So you can add those things. So you define the materials, saying that we ensure that the equations are all fair. And boundaries. There's only one boundary, which is captured by the multiphysics option. When you add these two modules, the pressure module, which takes care of the fluid, and the solid mechanics module, which takes care of the solids. I think in the the latest version, I believe it is called as the structural mechanics module, and for solids, and acoustics module for the fluids. So even there's only the names that have changed, but it's the same thing. The boundary or this multiphysics option automatically appears when you choose two different domains. So here, that's what is showing up. So far we have drawn the geometry, we have assigned the equations. Then comes the machine. Okay. So by default, I said I'll go with the predefined normal, fine, and so on. But then comes, how do you tell the discretized geometries or the discretized elements that you need to follow this periodic nature? Otherwise, we are not solving the eigenvalue problem in the way that we want to solve. Right now, the eigen business has not come yet. We have defined, we drew the geometry, we defined the equations, and we discretized it, and we want to ensure, when you say predefined, some mesh will appear, but we want to ensure that periodicity also prevails. So what I do is I do this mapped mesh. So I choose 3 faces from which have the common corner. Okay? These three highlighted ones in blue. Okay? So which roughly are coming from this particular point. Now, and then I distribute, I will say that in each of these edges divided along, say 12 or 15 or whatever, 12 to 15 is a reasonable number based on my experience with even helices and chevrons. Then I'll convert this mesh. Okay, then you will get the mesh on these faces. Once you get a mesh, what I'll do is I will okay, on the right side, when you right click on the mesh, it gives you a fairly lot of options. Okay, there's copying option, copy face, modifying, then boundary generators, a lot of options. Typically, we don't need to use all of them. I'm going for the copy options. I've just said on one face how that I need 12 elements. Okay, I think it's taking a while. Now you see the screen. I said on one face I'll need 12 elements. That's what we said here. Right? And then I've meshed the faces. And then now all I'm saying is I'm going to copy what is on one face to its parallel face. Copy from one, and one of them is called the source, and automatically other is the destination. And I do the same thing for the remaining two pairs of faces. And then I'll say whatever is in the interior, you can go with tetrahedral. And how did I get this free tetrahedral? Just right click here and you will see free tetrahedral, and even if you want some boundary also. In fact, that's how I generated mapped. Okay, so that is all we have. All we wanted to ensure is that once we discretize, I just want whatever is happening on the left, I want the same thing to happen on the right. Same thing with front and back and top and bottom in this case. We have it. So now we meshed it. And then comes study. So let me minimize the other things. Now I have study. So in study, how do we do it? You just right click, and when you add study on the top, okay, on the top here, I guess it shows up now. Yeah. So when you add study, you choose the eigenvalue computation. You choose frequency domain, and in that you choose eigenfrequency. This one appears. Okay, we would need to compute eigenvalue. Once you say eigenvalue, you would need, it comes with a default option. And what we have noticed is ARPAC does a reasonable job. The remaining options, I want to search for 1 megahertz, or eigenfrequency is around 1 megahertz. And you can actually tune if you want to meddle with the way COMSOL works. You can actually as well do that too. The best way and the smoother way is that you choose a larger real part, because all we are right now interested in is the real values of these eigenfrequencies. And the settings which I have given in the slides, in the solver configuration, you go to the eigenvalue solver and you feed in the same. The intricacies as to why should I do these transformations, okay, enter the transformed value, why should I choose the closest in absolute value, is clearly given in the manual of COMSOL. My objective here is to ensure that you compute the band diagrams in a reasonably quick fashion following these things. Okay, and whatever settings I have given you in the slides and in the paper also, these are exactly the same. And then comes the sweeping part. Okay, you please do the following. Whenever you put periodic boundary conditions, you put them as kx, ky, and kz. Okay, I chose it as on the top. The name of the file, if you can read, is T is symbolic of gamma. That's why you choose gamma. Gamma R is a diagonal. In the Brillouin zone, it is a diagonal. These are the points along the body diagonal, or the line between these 2 points, gamma and R, is the body diagonal, where the components of wave vector, x component, y component, and z component are all the same. That is why I put here as kx, kx, kx. Okay. Otherwise, if I am going along gamma x, I will put it as kx, ky, kz. Ky and kz will be 0. Kx varies. Now, kx, ky, kz are all the same. and I need to vary it from a set of frequencies, a set of wave numbers rather. And I'm going from the edge of a Brillouin zone and set pi by a. So I'm asking it to compute for n is I think 15, or let's go to parameters, and I chosen 20. So I've asked it to go for about 20 different waves. So let me go to the parametric screen. So that's what I have. And once you do that, you simply click compute. And this solution took about 10 minutes, okay, back in the day. I think this can be a little faster now. And once you do that, you identify, you say, we are computing global values. So go to the results under derived values. I didn't say that you're doing global evaluation. When you do that, just type in, I have chosen air as a medium, so that's why I've divided by the phase speed in air, 343. Okay, and I get my frequencies. And once you get it as a table. Then you say, either you can plot it here, say it as 1D plot group. Under results, you can say 1D plot group. And under 1D plot group, you can say I need a table graph. And I get let's get the set of bands around one path of the irreducible grid also. Okay, this is one of the simplest cases. So now let me show you a slightly advanced version of it, which is the chiral version. Okay, I hope, yeah, now you can see. Everything else is the same. I wanted to draw a geometry of a helix. I drew it, I gave it all the parameters. Okay, so there's no need to go for, then I assigned the materials. I chose again the same set of materials on the left hand side. Then the solid was the helix, or the helix was solid. So I've assigned it, the solid was helix, and the remaining thing inside the cube was fluid. So I did the same things. For the fluid, I assigned pressure acoustics. For the solid, I've assigned the solid mechanics. No problem at all. The unit cell must be periodic. Okay, now it shows it for you. The unit cell is periodic, so I've done exactly the same thing. I chose a bunch of pair of opposite phases. I've ensured periodic boundary conditions for the fluid, for the unit cell. But let us remember here, unlike the previous case, a part of the solid is also on the boundary. In the previous case, the sphere was a solid and it was nicely sitting in the center. So I didn't have to do anything when I was doing the solid mechanics. There were no boundaries. So, but here, part of the solid is touching the top and bottom faces. Okay, so I need to account for the periodicity here as well, and the equation remains the same. Okay, it's Floquet periodicity, it's the same thing. Just that you must realize that the solid is also now part of the unit cell, or the scatter is also part of the boundary of the unit cell. All right, then the multiphysics option, you can use the multiphysics option to ensure that you have the boundary conditions. And you can see it's the traction continuity and the velocity continuity. Velocity continuity normal to the interface and the traction continuity. And again, the same discipline must be followed when you do the meshing. Okay, I'm using a mapped mesh for these adjacent pairs. Remember, I'm doing in case of the sphere, this face, all three faces with a common corner were the same, but here it is not. So when I map this, I will choose the other two ones, okay, and distribute them. I think it appears on your screen now. Yes, it shows up on your screen now. So I've carefully chosen two faces and I first discretized them. Because there is an element of solid also there on the top and bottom faces, I chose to work in a slightly different style. Okay, then once I discretized them, I copied them to the parallel faces. Okay, the same thing I do for the other face as well. Okay, then I said free quadrilateral kind of meshes on the bottom face. Okay, I'm playing it differently because here my scatterer is part of the boundary. It is if the same sort of things are occurring on the vertical, so say this vertical, let your screen come to my screen. Yeah, if my faces with normals along X and Y were same as the face with the normal as the Z, I don't have to do much, which was the previous case. Now I have to take care a little bit more because I can't directly say whatever is happening on this left hand side edge here on the bottom will happen on the right hand side edge on the bottom face. There will be a difference, slight difference. Okay, geometrically, not saying with respect to the field. Field wise, they should be the same, but geometry wise, there is a difference. They're not symmetric. So then I converted whatever I've done so far into manually into meshes, and then I've already introduced the quadratic mesh on the bottom face. I've simply copied them just so that my periodic floppy block periodic boundary conditions are ensured. And then inside the domain, I've set everything as tetrahedral mesh. That completes the meshing procedure. Okay, why should we be careful? We should be careful because this is how the theory of finite element should be translated into COMSOL. Okay, COMSOL already knows it. It is our way of knowing the software and feeding it correctly. Because even if you right click here on the mesh, you see it provides us with a lot of options, a lot of them. There could be other ways of solving the same problem, but this is the way I've validated and performed computations. And after that, the business is the same. You sweep along a particular path. You ensure that your solver settings are in place. Okay, the solver configurations, eigenvalue solver, and then in this eigenvalue solver, the settings, you ensure them, and then the rest is the same as what we just saw earlier. I'm getting a lot of bands. In fact, this is the case of local resonance. So I guess with these two examples, which the files of which I will share to you, you would be clear in handling complicated geometries as well. So now let us look at a simple two-dimensional case of transmittance calculation. I know I've slightly gone past the time, but I'll try to wind up in the next 5 to 10 minutes. So I want to compute the case of steel spheres embedded in epoxy. So first I've defined a lot of parameters. It's always nice to work with parameters instead of numbers. Okay, so I drew my geometry. Everything is the same as before. I drew my geometry. On the left and right hand side, you see this, the leftmost and the rightmost. Those are the regions I'm going to assign as PML. For now, it is just a rectangle. You assign the material. This is steel. Okay, now it appears for you. And then I'll say the rest is epoxy. So it's a case of solid in solid. Okay, then I'll put water in the remaining because that is where I can send pressure wave. It just gets a little easy. Okay, and wherever there is water, I'll choose the pressure acoustics. Okay, that is all you see here. There's nothing. Wherever there is water, yes, it's appearing on your screen as well. The domain equations you have seen, by default, they are the Helmholtz equation. And now I'll define a background pressure field. How do you get it? In the domains, right click and you say background pressure field. This way, right? So you have it in the background pressure field. I'll define my magnitude. Since I'm doing transmittance, I'm only interested in the ratios. So the value actually does not matter unless any non-zero value should be fine. Then I define the wave direction, kx, ky. That is it. Then you're good with assigning the fluid. The boundary part, I want floppy block periodicity on the top and bottom because my wave is going along the x direction. I want geometrically it should be the same on the top and bottom. And that is what I'm ensuring here. Okay. So equation also, you can click on equation and you can see what is the equation that is there. So we have sorted the fluid part now. Let's look at the solid part. the solid part. Then you ensure now we have steel in epoxy, so everything is solid. So when I click on solid mechanics, I've already selected, yes, see that I've already selected all the solids. Okay, the equations are the same. The boundaries, there is a periodic boundary at the top and bottom. So that you ensure. How do you ensure? Right click on boundaries and go to floppy block periodic boundary conditions. Okay, you say periodic condition. Okay, that's what we need to choose. Right click and you will get that. And once you get floppy in this, then you choose floppy periodicity. So we have defined the boundaries as well. We have already ensured the wave here. In the pressure acoustics, there's a background field pressure that is defined. There's a number there, so the wave is already incident. Okay, you can as well try defining the wave externally instead of in the domain. That is also one way to do it. Okay, the boundary between the solid and the fluid, which are these two. Okay, if you click the multiphysics option, which COMSOL automatically recognizes, the equations are already taken care, continuity in velocity and traction. The meshing discipline, once you are familiarized with the calculation of band diagrams, you now know the drill. Okay, first you get to some predefined version and then you choose edge. Okay, how do you get edge? Right click on mesh, you get edge. There you go. Okay, you choose an edge element and then you tell what is the size, how much do you need, and so on. And then I'll copy this edge to the opposite edge. Why should I copy? Because I want to ensure floppy block periodicity condition. That's the way you are talking to the finite element interface. And the rest of the domain, and say it is as some free triangular. If you want quadrilateral, you can go for it, but two-dimensional we're solving, so that's why free triangular. Okay, and then I can refine the meshes by choosing the size. On these, it will have one size, and then okay, you see I have two sizes. I'm saying externally, in the domain you have a particular size, and in the second domain you have a different size. So that finesse on control of the size of the mesh is also there. Likewise, I'm going to map for the fluid. I'm going to map the same thing. Previously for the solid we used edge mesh. Here also you can do the same, or you can try using the map mesh. Okay, mapped is something which we have used in band gap calculations, which is why I've invoked it. Okay, the same thing, use the distribution. Now this gets fully meshed. Okay, and study wise, you choose when you add study. Where is this? In the top side, on the top menu bar, and you say add study. You say add study frequency domain. That is all. Once you do that, you're going to ask it to compute for a range of frequencies, F1 and F2 or something, which I've already defined, and NOF is the number of frequencies, and solve for it. I think this solution took about a few minutes, 10 minutes if I'm not wrong. Here it is, 6 minutes. Okay, unlike the eigenvalue calculation, there is not much to play around in the configurations. The default configurations would do the job. So we solve something. What did we solve? We ideally should have transmittance. It is not clear. How do I compute now? How do I get my values? So before I began, I did define under component. I did define a set of things. I defined a reference, okay, saying that this is where I'm going to compute my reflected pressure. Okay, then this other domain, other interface on the right hand side, I have said that is where I'm going to calculate my transmitted. So far I'm just calling them. How do I compute? I'm going to do some integration of pressure over this boundary. Those are the third and the second, the fourth and the fifth options you see on the left hand side, the left hand side menu. Okay, and on these I've already defined what should be computed. I predefined some variables. I want to calculate reflectance or reflection coefficient or transmittance or transmission loss or transmission coefficient. I've already defined them. Okay, you can right click define and variables, and that is it. And do I ensure that there's a perfectly matched layer? I have introduced an artificial domain and told that this is a perfectly matched layer. How exactly does this perfectly matched layer works is something given by, you can refer to the paper by Berenger. Okay, the difference I'm specifically held this part towards the end of this assigning of where do you compute and how do you define transmittance, because largely otherwise the computation is roughly the same. You define geometry, materials, the domain equations are all the same. So you introduce these variables, whatever you want to compute. You want to have a different expression, you can have it, which is a custom defined one. And you must tell the software, hey, listen, these two are the perfectly matched layers. When you the right click, you actually get this. When you right click on artificial domains, you actually get this perfectly matched layer. Okay, and since you already defined them, I have computed them, and I have plotted them. I've removed whatever on the derived values. You can right click and you can evaluate point evaluation or even a global evaluation for that region, and I directly have plotted it here. Okay, you see I've plotted transmittance versus frequency. There's a minimum transmittance in a particular spectral regime. Okay, the same thing I'll try to now walk you through what my student has recently done. Siddharth, remember that good old wood pile structure that we saw, a bunch of wood arranged in at 90 degrees in each layer. It's the same thing is done, but this involves a slightly different kind of machine. Okay, that's what I wanted to introduce. You draw the geometry, you define this PMLs and so on. So under definitions, there's variables and artificial definitions, perfectly matched layer, everything is there. Okay. I wanted you to focus on the domain equations are the same. So the meshing wise, I did something different. He first said there's a size, then he chose swept mesh. You're going from 2D to 3D. In the PML, he wants to ensure the wave does not go left or right. He wants to ensure that the wave goes just in one. Once it comes, it should only die, but the direction should not go. So that's the reason he chose a swept mesh. And in that, he went in for more options into the, how do you discretize? We just discretize it finer and finer and finer. Okay, and then he sized them too. And then the rest of the domain, he said, let me go with pre-tetrahedral, and then he has defined a particular size. Okay, so this is one more way of doing the same thing. Okay? And this is a complicated. First, I've shown you a simpler version, a complicated version of the same thing. Sophisticated, if you want to call it. The computation remains the same. The way you do your post-processing to get your results is also the same. Okay, this may take a while to pop up. Okay, this is done with a little more, not the best of the refinements, but you still see some band gaps being populated. When you have air, I think you will end up with certain some of these spikes. This can easily be overcome by choosing finer mesh size. But let's see, if you go for a finer mesh, the computation time is going to increase. So that's something which must be kept in mind. So I think I've covered largely what I thought should be covered when it comes to identifying the band gaps and the transmission or the reflectance. Okay, these transmission loss and reflectance, these are certain things which are handy when you do not just phononic, when you study phononic crystals, but any of the acoustic metamaterials. Invariably, when you say an acoustic metamaterial, you are bound to compute transmittance and reflectance. So these two are very handy. So which was the reason the talk might have gone a little longer. I apologize for that, but I wanted this to be in completion. So with this, I think Antis and Nina, I'm done. So I've essentially told the my audience what I wanted to convey. So thank you.
Thank you so much, sir. I feel that actually this is such a good and informative session. So thank you so much for that. So we have some good amount of questions in the question box. So maybe we will take some of that questions. So I will read
Okay.
the questions for you. So, dear professor, please suggest some books, especially from the introductory to advanced level on phononic crystal, and metamaterials.
Okay, one such reference, see, I had the same question when I started with. If you want a book on phononic crystal, you can refer to the book by Damier, Pierre Damier, I believe, P.A. Damier, he's from Arizona State. If you want to know the intricacies of computation, analytically, you can refer to my PhD thesis. There's an appendix where I put all the theory in detail. Whatever theory we are talking with COMSOL software, the same thing is there. As such, you learn things on the fly. I mean, I think I first referred to the book by Rose. It was not on phononic crystal, but it has a good amount of mathematics. Some of the good books to start with, but these books cater to solids. If you want a good book on fluids, for example, a good place to start with for both fluid and solid is the book by Auld, B.A. Auld. Yeah, I think this is a good. Kinsler is one standard reference which is used for acoustics. For acoustics, there are a few books. The one by Samuel Temkin is one. Something with David also is good. I don't recollect the book, but I can put it as a last slide as reference books and send it when I send the slides.
Yeah, thank you, sir. And one more question: what type of materials are used as periodic structure in phononic crystal? What are the practical applications currently undergoing based on phononic crystal, and what are its future scopes?
The scope is huge. One such thing is, I think I try to put together in this slide. This is only, I don't know if you're able to see the slide. Let me see audience view. Yeah, at different scales, people are working. Okay, and people have used different materials at all these scales: ceramics, polymers, and metals. Okay, we recently done in micrometers using metals and ceramics at millimeter scale. I've also done the helicals thing, which is so a lot of work at different scales using different kinds of materials has been done. It is now more on inverse problems. The current latest work is more like I want the band gaps on this particular regime, say 1 kilohertz to 5 kilohertz. I need a band gap. So what should what should be the choice of my materials? What should be the choice of geometry? What should be the choice of lattice? So that is the current state. When you're talking with respect to applications.
Yeah. So we have one more query. Thank you so much for this lecture. I would like to know that is it possible to add impurities through doping in this photonic crystal in COMSOL?
Yeah, you can always add. In fact, I have not shown that deliberately. One of the work which I said is of my which we did with my student. Like this one. Let me show you this geometry. Where's geometry here? Yeah. Yeah, you see the geometry. So what I'm not showing here, but what he has done is in each of these cylinders, he has put in one more cylinder. Towards studying locally resonant crystals, he has put in one more cylinder in each of these. Okay, I guess now you can see the same thing. So in each of these cylinders, he has put in one more cylinder, and yeah, so long as you are periodic and all, it should be fine. But what you cannot be doing is, let's say you want to compute, let's say you see my screen now. Yeah. So you see what is a waveguide here. If you want to do this kind of computation where you remove or you specifically remove the fourth row, third column array, third column scatter, that case you must use this exact geometry as it is and then choose your PMLs and all appropriately. But you must choose this domain only. What I have shown you is an what do you say state level 3 or a level 4 kind of computation. But if you want to study a specific case, you have an array and you are either taking out or you're replacing one particular cylinder, then you have to choose the exact identical geometry. There's no question of reducing the geometry. That is the only difference. Otherwise, rest of the things are all the same.
Yeah. Okay. Thank you so much, sir. One more query. The meshing used in the simulation seems to be very coarse. Is it okay to use that coarse mesh?
It is not okay. I mean, we see if I had chosen, let's go there again. If I had chosen, let's choose a different one. This is Sweden. I have deliberately see if you see in some of the other problems, I have not the global evaluation. Where is this latest one? In here, so if you see here, I have removed the results. Yeah, on the left side bottom, I have removed the results. Originally, we had computed it and ran it for I think a few hours. That was done with very fine mesh. And if I can't actually open and run through that because then we can't do this. It'll take a while. So just for the purpose of demonstration, where is mesh? We have chosen sort of a coarse mesh to represent. This problem would actually be okay. You see the cylinder is sort of appearing as an octagon or I don't know what is it called, decagon. Now you can actually further refine it further such that it resembles more, even after you discretize, it resembles more like a circle, and then I'm sure your results will be much refined. It's not okay. Just for the demonstration, I wanted you to know what is a swept mesh, how do you feed it. I wanted you to know how to talk to the software. That was the objective here.
Thank you so much, sir. One more query. How phononic crystal is different from photonic crystal? At what scale phononic crystal works as photonic crystal works at nanoscale?
Okay. First things first, you see this slide. Phononic crystal is about elastic waves. Elastic waves can be in solid as well as in fluid. Okay, this is physically representing, we are talking of atom level atom or a collection of atoms vibrating together. Photonic crystals is referring to the study of electromagnetic waves in again the similar kind of periodic medium. So there are two different hands or two different rooms, I should say. Here you're talking of elastic waves. There you're talking of in photonic crystals, you're talking of electromagnetic waves. And in both the cases, whether it is photonic or phononic crystals, people have done work in various scales. Okay.
Yeah, sir. Actually, we will take one more query, which will be the last one.
No problem.
There are so many queries. So, photonic crystal and how simulations can be beneficial for research in that field, especially COMSOL.
Well, I must say I have not done anything related to neutron to date, so I would not be the person to comment on it. Phononic crystals have otherwise been used for a lot of sensing liquids, especially in microfluidics. If you search for phononic crystals in microfluidics, you will actually see where people have sensed different chemicals, try to tell whether it is poisonous or the viscous nature, and they've also measured properties that they have done. I personally am not aware of. I am not aware of it.